Hello and welcome to this presentation on MATLAB to iPhone made easy. My name is Bill Chow, and over the next 40 minutes I'll be showing how you can take your MATLAB algorithm and run it on your iPhone or iPad. As you're working in MATLAB, you're writing scripts and functions to perform data analysis and visualizations, develop algorithms, and create complete apps that include graphical user interfaces. So how do you take all of this and run it on your iPhone? In the workflow that we're going to talk about today, we're going to take just the numerical algorithm that we've developed and generate readable and portable C code from it. Once we have the C source code, we'll integrate it into a new or existing iPhone or iPad app running in Xcode, an integrated development environment provided by Apple, and then Xcode will compile and download the app onto your iPhone. For the latter part of the process, we're going to assume you have experience working on iPhone and iPad apps with an Xcode. As I mentioned earlier, the code generated from MATLAB is going to be part of the overall code base of the iPhone or iPad app. There's going to be a lot more other code running in the Xcode project to make your app run correctly on your iOS device. So let me show you the end result of an app running on my iPhone. So switching over to my video feed, you can see an app that's running on my iPhone. This is the Geo Gravity demo that's provided by Apple. The teapot on the iPhone is balancing itself as I rotate the iPhone around. The app knows the direction of gravity using the data from the accelerometers. Now as I tilt the phone, the teapot will turn as if it's resting flat on my desk here. I can tilt it up and down and in all sorts of directions, and it's still doing its job well. So in this app, the data from the accelerometers is filtered by a simple low-pass filter before it's used to balance the teapot. We can design our own filter in MATLAB and use it in place of the default low-pass filter. So switching over to my Mac, here we have Xcode running already with the project all set up. So here's the default low-pass filter that's provided by the app. I'm going to go ahead and comment the default low-pass filter out, and in its place I'm going to replace it with a call to the low-pass filter that's been generated by MATLAB. It's already been integrated into the project, so now I'll go ahead, I'll build the project and download the new low-pass filter into the app running on the iPhone. So switching to my video feed again, you can see that the teapot is balancing much more slowly. I intentionally changed the cutoff frequency of the low-pass filter to just 0.5 Hz. So any movement faster than 0.5 Hz will be rejected. Hence, you can see that the teapot is balancing very slowly as I tilt the iPhone around. So this is the end result that I'll demonstrate today. Let's head back to the presentation. So coming back into PowerPoint, for the rest of the presentation, I'm going to break it down into two sections. In the first part, I'll show the basics of generating C code from your MATLAB algorithm using MATLAB Coder. We'll take a look at the challenges of manually translating MATLAB to C and introduce the recommended two-step workflow for automatically generating C code. And in the second part, we'll dive into integrating the generated code into your iPhone or iPad app. So let's dive into the first section. So to start off, you've got some MATLAB algorithm that you want to run on your iPhone. Your existing process might look something like this. So you start off with an algorithm that you've designed in MATLAB. Let's call that V1. And at this point, you'll need to recode it. Either you or another person will need to recode that into C, and we'll call that V1 of your C code. You might need to iterate a little bit on that piece of C code and then integrate it into your app and then run it on your iPhone. Of course, once you've made changes to your C code, you may need to iterate to bring the changes that you've made in C code back into your MATLAB algorithm. You might also need to test and verify that the C code matches the behavior of your original MATLAB code. And once you've made changes to your original MATLAB code, with this iteration, we'll call this this updated MATLAB algorithm your V2. Now, of course, as we all know, once projects get started, things could change in terms of new requirements being implemented, being added to your project, and so you might need to update your MATLAB algorithm to compensate for that. So we'll update our MATLAB algorithm into v3, at which point we'll then need to recode that into v3 of our C code, which will then run on the iPhone. So with this approach, because these two languages, MATLAB and C, are inherently different, there are many functional and behavior differences introduced into your design. So the primary problem with this approach is that you have to maintain two separate implementations that are not automatically in sync with each other. So if requirements change, as I was talking about during development, it's quite inefficient to go back and modify the C code, then test it all over again to ensure the functionality is the same as the original MATLAB algorithm. Coding errors are usually introduced during the manual translation process, leading to longer testing times and no guarantee that all bugs introduced are caught. And finally, the entire process is time consuming and costly, as it's expensive to maintain not only separate algorithms in two different languages, but also separate test benches in C that may not get implemented. With automatic translation of your MATLAB algorithm to C, you spend much less time writing and debugging low-level C code and more time developing and tuning your algorithms. So once you're happy with your MATLAB code, you start by generating a MEX file that automatically and bringing it back into MATLAB to verify the compiled execution. From there, you can generate source code and then integrate it into your app. With this approach, you maintain one golden reference in MATLAB and get to C code much faster. Having a single reference makes it much easier to make changes as requirements change. You also get to test it more systematically and thoroughly to account for more real-world scenarios. So having given you that introduction, let's now take a look at a simple demo that introduces the basics of MATLAB Coder. So here we're inside of MATLAB, and let's say I'm creating a simple function. All this is going to do is multiply two inputs together. Let's say C equals A multiplied by B. Two inputs. And let's save that. I'll call it my mult. And at the same time, I'm going to create something very simple, and all it's going to do is call my function. I'll call that my test bench. So with these two functions, I'm going to run this. I'll run my test bench, at which point I'll call my function, and it's going to multiply two inputs, 10 and 20 together, and the expected output is 200, as you can see here. So at this point, let's say I want to generate code for my mult. To start that process, we can open up MATLAB Coder app, and we'll call it my mult. So now here is the MATLAB Coder project window. One of the first things we need to do is tell which file we want to generate code from. So we can drag the file that we just created, mymult.m. And before we can generate C code, we need to define the data type and size of our two inputs. So automatically detected that we have two inputs, but now we have to define it. There's a couple ways to do that. We can start specifying the data types from this little menu here. It could be doubles, int32s, it could be structs. Another way to do it is we can define by an example. But one other thing I'm going to show you is this auto-define feature. So what this is going to ask you for is a file that's that will call the function you're trying to generate code for. So in this case, I'm going to specify my test bench. I'll click run. At this point, it's actually going to run my test bench, and then from there, it'll be able to infer the data type and also the size of my function. So I'm going to use the proposed types, and we're all set with that. Now we can go ahead and we can build. So we were able to generate a MEX file from that, and if we wanted to, we can come into my test bench. The The generated mex file is going to be the function name underscore mex, and I can run my test bench again, and we can see that the generated mex gives us the same answer. So with a more difficult or a more complex example, you want to run through a couple more test cases, but let's say everything works as we expect it to. So now let me go ahead and just generate C code. So here's the generated C code with my mult. It's fairly straightforward. It's going to return A multiplied by B. My two inputs, A and B, are here, as you can see, and these are all type double. I can also come in and take a look at the original MATLAB code. If I hover my mouse over, I can see the variables and their information. So this one, our output is of type double, and it's a single element. It's a scalar. Similarly, I can hover over A and B, and I can hover over the operators as well. So here it's going to tell me the output of the output information of A multiplied by B. So that was pretty good. Now coming back, what if we wanted to change things up a little bit? So we've been multiplying two single elements. So without changing anything in my mult.m, what if we now change the inputs to be multiplying two matrices? So in this case, my two inputs coming in are going to be two matrices. So now if I run my test bench, you'll see that my output is of size 3 by 6, which is the result of multiplying two matrices, a 3 by 4 matrix by a 4 by 6 matrix. So now I can go ahead and generate code again. Actually, I need to change one thing. So in my overview, I've specified the data type and sizes to be singular. So now if I run my test bench again in using the auto-defined feature, it's going to find the updated data type and sizes. So I'll specify that again, and we can build. So now here you can see with matrix multiplication we have our three nested for loops, and this is going to go through and multiply our two inputs A and B together and send our output C back. So that was pretty straightforward, but as you'll see in our generated code, there's quite a number of different files here, and with these rt, get inf, and all these other files here, these were generated in order to support special numbers like infinities, not numbers, and other things of that nature. So if we come back, close it out, we can make some changes to our code generation options. So for one thing, we can turn off support for non-finite numbers. Close that out, and we can generate code again. So now you'll see that we still have the same generated code as before, but we remove some of those extra files that we don't need for our application. So I hope this simple example gave you an idea of the process for generating code. So the algorithms you create probably won't be as simple as the example that we just saw. To successfully translate more complex and real-world algorithms, we recommend this two-step workflow to use MATLAB Coder. So in the first step, you need to prepare your MATLAB algorithm for code generation. You'll first assess code readiness of your MATLAB algorithm for code generation. Then you'll update your MATLAB code to introduce implementation considerations that are needed for C, and you'll need to use the MATLAB language features supported for code generation. So once you're done with this initial update of your MATLAB code, you'll test it to see if the code that you just modified is ready for code generation using default settings. So if you're successful, MATLAB Coder will generate a MEX file, and if not, you'll need to iterate to get your algorithm to a point where you can successfully generate a MEX file. So once you've generated a MEX file, you'll move to the second stage where you can iterate to optimize the C source code for your purpose. At this stage, you can optimize the generated C code for look and feel, memory, and speed, or you can optimize the MEX function for performance. So the first step in the workflow is prepare your MATLAB algorithms for code generation. What this really means is to take a look at some of the implementation considerations that we rarely pay attention to when coding in MATLAB, but are required for any C programming. So what are these considerations? So let's take the example of the simple function foo.m that we were just looking at that multiplies two inputs. In MATLAB, this single line of code can take different meanings depending on your input. So this could mean element by element multiplication, which is the first case that we saw. This could also mean a dot product, or it could be a matrix multiplication if the two inputs are matrices. Also, these inputs could be different data types, and it could be real or complex. So as you can see, MATLAB is a powerful algorithm development environment precisely because you don't have to worry about the various implementation details. However, when you write C code for this simple line of MATLAB code, you have to explicitly specify what this operation means. So this could be a single line of code that returns b multiplied by c, or it could be more complicated with this 11 lines of code that multiplies the two matrices together. So when you're thinking about implementing your MATLAB algorithms in C, you have to pay close attention to how it'll look like in C. So there are essentially four types of considerations that you need to be aware of. The first is polymorphism, and as we saw in that simple demo, the same piece of MATLAB code can be used for element by element multiplication and matrix multiplication. So for C code, you'll need a separate prototype for each of these different forms, so we need to think a bit about this. The next is specifying whether your data is statically or dynamically allocated in memory. So MATLAB is dynamically typed so that you'll never need to worry about declaring memory for the data you create and use. On the other hand, C is statically typed, so you'll always have to explicitly specify what the size of your data is, or else use dynamic memory allocation using commands like malloc. Then there's a difference in processing arrays. MATLAB uses compact optimized single line expressions, whereas C code uses for loops. There's also a difference of zero-based indexing in C versus one-based indexing in MATLAB. Finally, you'll have to specify data types for your input-output arguments as well as your internal variables when you're coding in C. So the effect of specifying all these implementation requirements is that 7 lines of MATLAB code for a Kalman filter can turn into 107 lines of C code for a specific implementation version. Having gone through that, let's take a look at a quick example of specifying implementation constraints. So the Newton-Raphson method is a well-known numerical algorithm for calculating the roots of a number. So I can find the fourth root of the number 256, and the answer is 4, as we expect. With this function that I created ahead of time, we can also enter a third argument that specifies a tolerance. So here, the fourth root of number 10 is 1.7783. So let's take a look at this algorithm. So in this algorithm, it takes var in. It uses var in to take at least 2 inputs from the user. And there's a possible third variable if the user specifies it. So in here, we'll see Newton's, it's going through some initialization, and it's going to actually call Newton's search algorithm. So let me open that. So this is the bulk of our algorithm, and right at the beginning there's some initialization. Here we have our initial guess. Looking further down, we have a big while loop starting here, and if you look through this, you'll see that this while loop will have a maximum of 50 iterations. And we're going to calculate the derivative of this input. So once again, I'm going to create a simple test bench, and all I'm going to do is enter the command that I was using. We'll call that my test bench. Now if I run this, we'll see that we get the fourth root of number 10 is 1.7783 as before. So going through, the first step is to assess how ready our code is. And so to start the code readiness tool, or we can use the code generation readiness tool. So here we can see that with this tool, it gives us an initial assessment of how ready our code is. And given the results here, it looks like our code is ready to use with minimal changes. Alright, so that's done. Let's open up the MATLAB Coder app again. And I'm again going to drag and specify the code that we want to generate code, or the function we want to generate code for. I'll use the auto-define feature again, and I'll use my test bench. I'll run, and I'll accept the proposed values for our inputs. We'll go ahead and generate code. So when we try to generate code, we see there's an issue with it. So if we clicked on this, it'll show us the line of code where we're having issues. And over here, it's saying line number 9, there's some problems with it. If we look further down the code, we'll see that the variable h keeps expanding within the while loop. So in C code, we need to explicitly specify the size of this variable. So to solve this problem, we know that the variable can have a maximum of 50 elements, since the while loop breaks out of here. So we can go ahead and explicitly set the size of this to 50 elements. Okay, so let's go ahead and build again. So it looks like we were successful. We've got our mex file, and coming back into my test bench, if we run my test bench, the answer is 1.7783, and if we now call the mex file, it's going to give us the same results. So look, that looks good. Let's go ahead and generate C code for this now. So here's the generated C code. So coming and taking a look at the header file, we'll see our function prototype and RT. Clicking on that takes us to the actual code for the Newton-Raphson algorithm. Coming further down, you can see it resembles the MATLAB code that we wrote, and here's that big while loop that we saw in the MATLAB code. So this is a good start. We generate C code for our algorithm, but let's see if we can make this more compact. So a lot of the code here is to support non-finite numbers like inf and not a numbers. So let's see if we can remove these supported files. Again, going into project settings, we can turn off support for non-finite numbers, and closing that out will regenerate code. So here it is. It's the same code that we saw before, and we remove those extra files that's needed for infs and not a numbers. So the code is cleaner, but is there more that we can do to compact the code? Actually, coming back to the original MATLAB algorithm, fine, actually right in NRT. So coming down here, you'll see that on line 25 we use the command find, and if you look in the C code, in rt.c, coming further down, there's quite a bit of code here that essentially corresponds to that command using find. So one of the reasons for these large number of lines of code is that we're using the find command. So MATLAB makes a large number of diverse functions easily accessible. Sometimes you run into code where a particular function is simply overkilling the problem, which leads to inefficient implementations in terms of performance and memory usage. So in this case, we're doing something very simple. So let's see if we can rewrite that line of code and generate less C code. So coming back, so for each iteration of the Newton search algorithm, the history array will be populated with a non-zero number. So this line of code is doing just this. So suppose we have this array of 5 elements. If we then type this command in, if we use the same format but now look for values less than 0.5, what we get is a number of elements that is less than 0.5. So in this case, with these numbers, there are 3 elements. So at the end of the day, all we really need is this number here. A simpler command to use would be the sum command, and this gets us to the same number. So instead of using find, let's replace it with this other line of code. I'll comment that out. So now that we rewrote the algorithm with the sum function, we should get the same answer and bypass the need to use the find command. So to test that out, again, we can go to my test bench. We can run that. Again, we're still getting the same answer, and that's calling our original MATLAB algorithm, not the MEX file. So now we can go ahead and generate code again. So with the regenerated code, if we go further down, we can see that down here there's definitely less lines of code. So now we're using probably about 5 lines of code to find the number of iterations. So we further streamline our algorithm. So in addition to compacting our code, we can also change the look and feel of our generated code. So if you noticed, our MATLAB algorithm was split between 2 files, an RT and Newton search algorithm. However, in the generated code, we only had 1 file, an rt.c. So we can make the generated C code have 2 files and emulate the look and feel of that original MATLAB file. To do that, come back to our original MATLAB algorithm, and we can enter this command. So this line of code does not change the behavior of the generated code, but it does tell MATLAB Coder to not inline this file in the generated code. So if we go and generate code again, you'll see that now we have 2 files, nrt.c, and looking into nrt.c, it calls our second file, Newton search algorithm.c. So using this option allows us to make the generated code closer to what we want. So I hope this demo gave you a good idea of the types of things that you can do to make the generated code the way you want it to be. So because of the various factors we need to consider when writing or generating C code, it follows that not everything in MATLAB would make sense for generating code in C. So only a subset of the MATLAB language is supported for code generation. So this is the subset that makes the most sense in converting to C. The supported subset is quite broad, and as a design engineer, you'd use many of these features in your algorithm development. The supported language includes all the standard matrix operations, the various data types, and different programming control constructs such as for loops, while loops, and switch case structures. There are more than 700 operators and functions from a few different toolboxes that can generate code, including more than 300 system objects that are part of the system toolboxes. So that was a short introduction to using MATLAB Coder. Let's take a look into the second part of our presentation and look at integrating the generated code into an iOS app. So switching over to my Mac again, I've got Xcode open and I've opened up Geo Gravity. So this is the original code that came from Apple. I've not made any modifications to it. And the first thing I'm going to do is just make sure that the app will run correctly on its own. So I've compiled and downloaded into the iOS simulator, the iPhone simulator here, everything ran correctly. Obviously, there's no accelerometer data that's coming into the app, and so the teapot is just floating around. So I'm going to stop that, and I'm going to change so that I compile and download it into my physical iPhone. So I'll go ahead and do that. So switching over to my video feed, here I've got my iPhone again, and the app, as I explained earlier, it's just the teapot is reacting to the data coming from the accelerometer, and the data will try to lie flat with respect to gravity. So the app is running correctly. Okay, so coming back to the Mac, I'm going to stop that. Let's take a look at the project here. So under Geo Gravity App Delegate, this is the part of the code that I'm going to change. Looking instead of here, you'll see that this is where we specify the low-pass filter. Right now, by default, we're using a basic low-pass filter. But at this point, what if we wanted to replace this with a low-pass filter that we designed inside of MATLAB? So that's something that we can do. And coming into MATLAB, ahead of time I created a simple low-pass filter. I'm using dsp.biquad filter, and this is from the DSP Systems Toolbox. And I've also done some other things. So one other thing I took a look at is I had the iPhone, I held it in my hands, I was twisting it around, and I recorded the data from the accelerometers, and that's displayed here. So in this first column, you'll see the first graph here is representing the data from the x-axis. In green, this is our y-axis, and then finally in blue is our z-axis data from the accelerometers. And what I've done here is using the filter that I designed, there's two things that I wanted to change. I wanted to see which filter order I'm going to use, and the other is what the cutoff frequency is going to be. So taking a look at these two variables, I've taken the input data that I recorded from the iPhone, and I applied the filter to it. So I applied two different types of filters. The first is a second order filter with a cutoff frequency of 2.5 Hertz, whereas with the three plots here on the right, it's the same filter, but I've changed the cutoff frequency to 10 Hertz. And I wanted to compare these two filters and see what the responses look like. So zooming in, the solid line here is our original data that was recorded from the iPhone, and you can see the solid lines are the same for both sets of filters, and the dotted line here is the output of our filters. So if we apply a filter with a cutoff frequency of 2.5 Hertz, you can see that it smooths out the response from our inputs. A lot of these low jagged movements are filtered out so that our output is relatively smooth, and you can notice too that there's a slight time delay, maybe 0.1 seconds or so. Whereas if we applied a filter with a cutoff frequency of 10 Hertz, the delay is much shorter. As you can see here, the offset is maybe 0.05 or maybe 0.03 seconds. But the other characteristic is that a lot of the movements are retained. So you can see that the output generally follows the shape of our input very closely. Of course, these very sudden movements are filtered out. Now, depending on how you want to design your filter and what your application is, you're going to choose the filter response that most suits your needs. So in our case, we want a smooth output, but we want to reject some of these more sudden movements as well. So in this case, we would want to choose a filter with a cutoff frequency of 2.5 Hertz. So this is the data that we see in the x-axis. If we now look again at the y-axis, it will be a similar story with a filter of cutoff frequency 2.5 Hertz. It's a smooth output response. Much of this jagged response is rejected, which is what I want. And again, with the filter at 10 Hertz, it we keep a lot of this jagged movement. So for our application and for our purpose here, we don't want this type of output. Instead, we're going to choose a filter with a cutoff frequency of 2.5 hertz. In addition to choosing the cutoff frequency, we can take a look at the response from different filter orders. So again, same deal. On the left column here, it's a filter. It's a second order filter with a cutoff frequency of 2.5 hertz. And on the right, it's the same thing. Cutoff frequency is again 2.5 hertz, but we're using a filter with 8 taps. Now, comparing these two sets of data, if we zoom in, the plot on the left is what we saw before. Whereas if we switched over to increase the filter to 8 taps, we see that again the output is very smooth. It's what we want. However, the time delay is much more. It's about 0.3 seconds or so, compared to maybe 0.1 or 0.2 seconds with a second order tap. Zooming into some of the other data here, let's take a look at the z-axis this time around. Again, for our purposes, we like this output which is smoothed out. We're rejecting all these little minor shifts, and with the 8-tap filter, it's the same output, but there's a much longer time delay, and there really is no tangible benefits for our purposes of going to an 8-tap filter. So in the end, we're going to choose a filter, a second order filter, and we're going to have a cutoff frequency of 2.5 hertz. So having done that, let's come back, and here I pre-built the library, pre-built the MATLAB Coder project. I've set all my parameters up correctly, and I'm now going to generate code for it. So here's the generated code, and looking at the header files, I'll have these 3 functions. My actual filter algorithm, and then an initialization and terminate. So looking at our actual code, you can see the inputs and the outputs. The inputs X, Y, and Z, and then the outputs X, Y, Z out. You can read through the rest of the code for that. And looking at the other 2 functions, in our initialization, we're setting some of the initialization code out, and then finally we're freeing the memory after we're done with the filter. So we generated code for that, and coming back here, our generated code is actually here. So I'm going to, let's see, open it up in Finder. So in order to integrate the filter to our app, these are the 4 files that I need. So I'm going to bring Xcode back, and actually I'm going to close the simulator. Coming back into Finder, I need to import that into my project. So just to keep things clean, I'm going to, let's see, create a new group. And coming over here, I'm going to import it into my project. So I'm going to actually not copy the files over to my project. I'm going to reference it, and using this approach, whenever I generate code again, this app project will be able to pick up the changes, and then we can very quickly do iterations, change the code, regenerate the code, and then compile and download it into our app and see what the changes are. So I'm going to click on Finish. So I've got the files that I generated. It's all here. Here's the header file. So we got our 3 functions. So in order to implement that, I need to make 4 changes. So the first thing I need to do is include that file, include our header file. Next, I need to put in the initialization code. So I'm going to type in that. And once the app closes, we're going to deallocate memory. finally, over here, we're going to comment out our calls uh, to the original low-pass filter, and instead we're going to call our filter Okay, so now instead of calling our basic low-pass filter, we're going to call the low-pass filter that was generated from our MATLAB algorithm. So that's that. Let's go ahead and compile and download it into the iPhone. So here it is again, and as you can see, since at this point we're using a cutoff frequency at 2.5 Hz, the teapot is moving very smoothly, and any sort of sudden movements are going to be rejected by our low-pass filter. So we were able to insert the code that we generate from MATLAB into our app and then run it on our iPhone. So coming back to the Mac, one thing I mentioned is that once you set this framework, you can very quickly start changing things and see how your changes react in our app. So coming back into MATLAB, I mentioned before that we were using cutoff frequencies of 2.5 Hz. One thing we can do is, just to kind of break our low-pass filter or change things so that it's more noticeable, I'm going to change the low-pass filter. Oops. I'm going to change it so that now we're going to build a low-pass filter that has a cutoff frequency of just 0.1 Hz. I'm going to update this, and it's actually going to run the script here, and I will change our cutoff frequency to just 0.1 Hz. So now that's reflected. Here our cutoff frequency 0.1 Hz, and coming back, this change by changing the variable in our workspace, we can now go ahead and regenerate code, and this is going to be picked up by MATLAB Coder automatically. So here's the same generated code. Of course, the only change is that we very quickly changed the low-pass filter cutoff frequency to 0.1 Hz. Coming to Xcode, that's again the change is picked up automatically since we're pointing to the file and we didn't copy the file from before. So without changing anything else, I can go ahead and compile, build, and download the app. So here it is again. Now you'll see that as I turn the app around, it's moving very, very slowly. And that's of course because we changed the low-pass filter cutoff frequency to just 0.1 Hz. So when we do that, essentially we're going to reject any sort of sudden movements. Any movements beyond 0.01 Hz will be rejected by the low-pass filter. And that's why this teapot is moving so slowly at this point. So with that, I hope I showed you gave you a sense of the workflow that you can use, where you can design your algorithms in MATLAB very quickly, generate code for it, and then download it into your app. So coming back to our PowerPoint and wrapping things up, I hope this webinar was useful for you to understand how you can take your MATLAB algorithms, generate C code, and integrate that into your iPhone or iPad app. For more information, you can always visit the product page, and a recorded version of the presentation will be made available on the public site within the next couple of days. You can also contact your MathWorks account manager to request a trial license. Here we can help with a guided evaluation where one of our highly knowledgeable application engineers will guide you through the product and walk you through the capabilities as it pertains to your specific applications and needs.